One of the things that makes Motorola's original definition of Six Sigma so important is that it distinguished between a long-term and a short-term view of the process. As you probably know, Motorola's original definition of Six Sigma took into account that over the long term, the process mean was very likely to drift from the target. In this video, I'm going to discuss this issue of the long term versus the short term, then go on to define process Z's and the long-term capability indices P sub P and P sub Pk, which are sometimes called process performance indices. Within Six Sigma, there are quite a few instances where a distinction is made between the long term and the short term. And some of the examples that we'll be looking at have to do with the calculation of process Z's, the calculation of these long-term capability indices I just mentioned, and also in Motorola's original development of the idea of Six Sigma. So the difference between long-term and short-term really has to do with whether or not you recognize that process means tend to drift over time. As you know, this idea that process means drift was key in Motorola's original definition of Six Sigma in the 1980s. And in particular, Motorola, based on Motorola's experience with its own processes, had decided that it was reasonable to assume that process means drift away from the target by up to 1.5 sigmas. Here, the sigma that's being referred to is the standard deviation of the process. So what this means is that over the longer term, the process mean can be assumed to change. So I'm now going to start discussing this idea of process Z's. And in statistics, the letter Z is often used to denote a standard normal random variable. So that's a normal random variable that has a mean of 0 and a standard deviation of 1. And in many situations in statistics, and some examples would include the sample mean, x-bar, and regression coefficients, when a statistic is standardized, it has a standard normal distribution, at least as the sample size begins to get large and the central limit theorem begins to occur. So what is standardization? Well, standardizing a statistic means that you subtract its expected value and you divide by its standard deviation. So for example, if you take x bar and subtract mu, its mean, and then divide by the standard deviation of x bar, which is sigma over the square root of n, you will get a random variable that's oftentimes labeled Z that will have a standard normal distribution, at least as the sample size becomes large enough that the central limit theorem takes effect. So what standardizing has done is it's re-expressed the original units in terms of the number of standard deviations away from the mean. So now if the value of Z is, for example, 2.1, we know that the statistic is 2.1 standard deviations above the mean. Six Sigma has adopted this idea and uses Z to denote the number of standard deviations something is away from the mean. It's really looking at the units in terms of the number of standard deviations away from the mean. Now specifically in Six Sigma, these Z's are generally used to represent how far away the specification limits are from the process mean. So what are the Z's in Six Sigma? Well, the Six Sigma handbook defines the following Z's. They define ZU for Z upper, and that's going to be the upper specification limit minus the process mean divided by an estimate of the process standard deviation. They also define Z sub L for Z lower, and that's going to be the process mean minus the lower specification limit divided by the estimate of the process standard deviation. So both ZU and ZL are both defined so that they will be positive numbers if the process mean is between the specification limits. The Six Sigma handbook then defines Z min to be the minimum value of Z upper and Z lower. And again here, x bar is the process mean, and sigma hat is an estimate of the process standard deviation, and the acronyms USL and LSL stand for the upper specification limit and the lower specification limit, respectively. Now, in estimating these Z's, the usual estimate of the process standard deviation is to compute R bar over D2. Here, R bar is the average of subgroup ranges, and D2 is the appropriate constant taken from the table of SPC constants. Now, what the Six Sigma Handbook calls Z-min actually usually goes by another name in practice, and that's Z sub ST. And here the ST refers to the short term. So what Z sub ST is it's the distance in standard deviations from the current process mean to the nearest specification limits. So, for example, a ZST of 3.5 means that the nearest specification limit is 3.5 standard deviations away from the current process mean. So a higher ZST is better. Now, what about the long term? Well, the ZST does not take into account the expected drift in the process mean over the longer term. It's just simply the current distance from the process mean to the nearest specification limit. Well, suppose we define Z shift to be the expected drift of the process mean over the long term from its current value expressed in standard deviations. Then after we take into account this Z shift for the longer term, we end up with a worst case situation where the Z in the longer term is going to be the Z in the short term minus the Z shift. And so now here ZLT is the long-term Z, and it's simply the short-term ZST minus the anticipated Z shift. So how do you usually select Z shift? Well, pretty much everybody defines Z shift in the same way that Motorola originally did, and that is that they take the Z shift to be 1.5. So usually the Z long term is the Z short term minus 1.5. Now this may seem a little bit too conservative, at least it does to me, because if your current process mean is already off target, you don't really anticipate that it's going to go further than 1.5 standard deviations away from the process target. And so to allow it to shift another 1.5 standard deviations may actually be too much. But whether or not Z shift should be 1.5 really depends upon what you want to convey. Another way to look at this issue is that if you're currently off target and you're not paying attention, you could easily have your process mean drift another 1.5 standard deviations away. But what is usually done in practice, no matter what the argument here might be, is to set your Z shift to 1.5. But in theory, you don't have to do that. You can set it to whatever you think is appropriate. So I've now defined the usual process Z's. They're the Z short term and the Z long term, and then the Z shift that connects the two. And these Z's are commonly calculated for processes in practice. In fact, one major company that I study requires that the Z be specified for every DMAIC project, both before and after the project has occurred. So they expect a short-term Z and a long-term Z to be calculated. And part of the way the project is evaluated in terms of its success is the impact that the project has on the Z's. Next, I want to talk about process capability indices because they also can suffer from a long-term, short-term kind of issue. So first, recall the definition of the standard process capability indices C sub P and C sub Pk. C sub P is simply the distance between the specification limits divided by 6 times an estimate of the process standard deviation. And the basic idea here is that we kind of consider that an entire normal distribution is within plus or minus 3 sigma. So this ratio is really asking the question, how many normal distributions fit inside of the specification limits. Now this C sub p does not take into account whether or not the process is centered, so it really should be interpreted as the potential capability of the process if the process is centered exactly on target. Now I think a more useful process capability index is the C sub pk, which does in fact take into account whether or not the process is centered. And what it is it's the upper spec minus the current process mean. So this will be a positive number if the process mean is between the specifications. And then the current process mean minus the lower specification limit. Again, if the process mean is within the spec limits, this is going to be a positive number. So we take the minimum of that, which gives us the distance to the closest specification limit, and then we divide by 3 sigma. The question that we're really asking is how many half distributions fit inside of the specification limits. Using the notation that we defined on the previous slides, the C sub pk can be defined as z min over 3, or equivalently the z short term over 3. Now based on what I've described in these slides so far, it might make a great deal of sense to define a long-term C sub pk by simply substituting the z long term for the z short term in the definition of the C sub pk on the previous slide. So what I'm contemplating here is that we just take this z short term and substitute the smaller z long term, thereby making the process capability index smaller. But this is not what is generally done in practice. And it's possible that this is not done because the approach taken would not work for C sub p, since the C sub p does not depend on the process mean. So for example, if we go back and look at the definition of the C sub p, it's never defined in terms of z's at all. The z's, remember, represent the number of standard deviations to the closest spec limit. C sub p is not defined that way, so there's not really a good way to redefine C sub p based on only using a z long term instead of a z short term. Now I also want to remind you that in these process capability indices, the estimate of the process standard deviation that's used is generally also the R bar, the average of the subgroup ranges, divided by the SPC constant D2. So what do we do for these process capability indices instead of substituting ZLT for ZST? Well, what we do is change the way we estimate the sigma hat. And in particular, instead of estimating sigma hat by R bar over D2, we estimate the sigma hat by using the regular sample standard deviation S, computed using all of the data. This sample standard deviation S is something you learned about in your basic statistics courses, and in fact, computing the standard deviation of the process this way is quite likely to have been what would be the natural thing to have done before you learned about subgroups and R bar and all of the rest of that. So let me explain what's going on here. So when I begin to teach basic statistical process control charts, I generally draw a diagram something along the following lines. Here's our process going along, but instead of being constant, I begin to put in the kind of process drift that Motorola anticipates. So the process may drift up, and then the process may drift down, and so on, but it's going along, varying along. And if you believe Motorola, then this process drift is going to stay within 1.5 standard deviations of the process mean. Now I think in the picture I've drawn, I'm showing a deviation that's bigger than that. But what I argue when I'm teaching statistical process control is that what you really want in constructing your control limits is the local variation in this process. What you don't want is this bigger variation. You don't want a variation that looks like this. I'm going to draw a line in here which is supposed to represent the process mean. You don't want to capture this kind of variation because in fact you want that variation to be interpreted by the control charts as being special cause. And it's this argument that leads us to using the range of a subgroup. Okay, so I may have, if I just pull this down here, I may have a subgroup of data points like this. So what we do is we take the maximum, and then we take the minimum, and then we compute the range, and that's going to be equal to an R sub I. And we do this for all of our subgroups where we sample through the process. And then finally we compute an R bar, which is just going to be the average. So it's going to be 1 over the number of subgroups from y equal 1 to m of the individual subgroup ranges. So then I explain that you can get an estimate of the process standard deviation by taking the R bar and dividing it by the special SPC constant D2. And all of this reflects the local variation in the process. Now, had you used the sample standard deviation, it is, of course, the square root of the sample variance. And what the sample variance is 1 over n minus 1. And it's a sum now that is based on the deviation of each point from the overall average squared. So this is the sum from I equal 1 to n. So what this squared deviation is looking at is it's looking at not only the local variation in the process, but also the variation all the way down to the average. The sample variance is going to be inflated by the drift in the process mean over time. Now, in the context of statistical process control, where you're really trying to set your control limits based on the common cause variation, which is the local variation in the process, the fact that the sample standard deviation captures the drift over time is a very bad thing. But if you are concerned that your process capability indices, if they're based on local variation, may in fact be conveying that the process is performing better than it will over the long term, the fact that the sample variance captures this change in the process mean over time suddenly becomes a good thing. So returning to the definition of the process capability indices, the concern is that the estimate of the standard deviation based on the local variation is going to be too small, which inflates the process capability index and makes the process appear to be more capable than it actually will be in the long term. And that problem occurs not only for the C sub P, but also for the C sub Pk. And so essentially what the idea here is that the local variation estimate of the process standard deviation is too small. It simply doesn't reflect what's going to be happening in the long term. So this leads people to define long-term process capability indices, which are also called process performance indices. And there are two of them denoted by P sub P and P sub Pk, which are the direct analogs of C sub P and C sub Pk. And they are gotten by just taking the formulas for C sub P and C sub Pk and substituting the sample standard deviation computed using all of the data for the sigma hat that was computed based on the subgroup ranges. So the P sub P becomes the difference in the specification limits divided by 6s, and the P sub Pk becomes the distance to the nearest specification limit divided by 3s. And once again, S is the usual sample standard deviation that you learned in your basic statistics course, but it's computed using all of the data, which should reflect drifts in the process mean over time. So this concludes my discussion of long-term versus short-term, of the process Z's, and of the process performance indices. The idea really has to do with whether you take into account drifts in the process mean over time. The idea of the Z's is that they are the number of standard deviations to the closest specification limit. That's the Z short term. The Z long term reduces that Z by the distance of Z shift, which is the amount that you anticipate that the process mean will drift over time, also expressed in standard deviations. And then we go on to define these two process performance indices, P sub P and P sub Pk, merely by changing the way we estimate the standard deviation to use the usual sample standard deviation, because it is in fact contaminated in a sense by drift in the process mean, which makes it more conservative with respect to capturing the process capability levels over the longer term.